All right, so I want to go back to definite integrals for a second. So close that stuff up. Let me take a look at something with you here. What if I gave you this one to do? What if we were going to do, we'll just make it an indefinite integral. Actually, no, make it a definite integral. Sorry, definite integral. So what if we wanted to add up, let's say, the area under cube root of x times square root of 1 minus x dx from, I can say 1 to, what would be a convenient one? 8. Okay? What could you do? Okay, you'd want to make u equal 1 minus x. Yeah, go ahead. You'd want to make u equal 1 minus x because we have to, right? We've got a 1 minus x under this radical. Okay, and we can't distribute over a radical, right? So we'd want to make a u substitution. So we'd let u equal 1 minus x. So what's du then? What's du? Negative dx. Okay. And if we try to make our substitution, then look what happens. So we're going to get the integral of, this becomes, dx is just a minus du, right? Okay, so that part's fine. What does that part become? Okay, but look at this. I'm going to clearly, I'm going to have to, that's not a complete substitution, and so I'm going to attempt to complete the substitution, right, by solving for x up here. I get what, x equals u minus 1, right? And so then I can try to, let's see, hang on a second here. So, yeah, I could try to do that, couldn't I? Right, I could try to make that substitution. I'd end up with a cube root of x, which I could make a cube root of 1 u minus 1. Was it 1 minus u? You're right, sorry. 1 minus u, there you go. Okay, so then I've got my cube root of 1 minus u, but look what happened. We had the same problem that we had before, right? Didn't help. Didn't make things any worse, maybe, but it didn't make things any better. And so there is no u substitution that's going to work, is there? Turns out this is an example of a problem that you can never do. There is no way, you can't analytically do this problem, this particular function. This is one of many where it turns out there's no antiderivative. There's no function possible whose derivative equals that. Yep.
So can that be graphed?
It can be graphed, yeah.
What would it look like?
Well, let's graph it right now. And that's what's weird about this is there's definitely, so we got to figure out a strategy for this, right? Because it can be graphed. The right question to ask is, can we do something with this? So let me pull up my fancy Desmos file that looks at areas under curves. Okay, so yeah, if we graph this thing, see what we get. So the function is that we're looking for an area under. That's going to be cube root. So how in the heck do I do that? I go down here, functions, miscellaneous, right there. So cube root of x times square root of 1 minus x. And we're going to add this up from 1 to 8. And so, oh, I guess I picked, that's not part of the domain, is it? That was dumb. You got to pick a different domain because this function's only defined for values of x less than 1, right? So let's less than or equal to 1. So let me, I guess I didn't really think about that part. Let's pick a new domain, but we have the same problem. Regardless of what we want our limits of integration to be, we've got the same problem. So let's go 0 to 1. So if we go 0 to 1, we still can't do the integral. It's not an integrable function.
So, but there still is area underneath.
There is an area under the curve. So if we let a equal 0 and b equal 1, there's an area right there, right? We can see it. Okay, and the answer is that. Okay, but, well, okay. You tell me, what am I going to do? What are we going to do here? How are we going to find this? How did they find it?
It's Desmos.
It's Desmos, you're right. You got a pipeline to the math gods, evidently, but how do you think they did it? Seriously, that's a very serious question. How does your calculator do it? When you do NINT, numerical integration, and your calculator gives you a decimal, do you think your Texas Instruments, how is it doing that?
Archimedes principle.
Archimedes principle.
Drop in water with a gravity cylinder. It goes up a certain.
Okay.
Two-dimensional cylinder.
Not quite, but you're not as far off as you would think, honestly. I mean, I could draw a logical connection between what's really done, but what do you think they do? What are the options? What are your options for doing a regular integral that we can integrate? Think about we know a trick now, don't we? Right? We know a trick in that we can find it using the fundamental theorem of calculus, but we've done this multiple ways. We did this in the past by using a bunch of rectangles also, right? No. What must the calculator do to give you a decimal answer? Some calculators actually will give you, like the TI-89 will give you a non-decimal answer. Like if we go back to one of our previous examples, just bear with me on this. This might seem unnecessary, but I really want to make a point here because there's a larger discussion you can have about this. As often happens with calculus discussions, this one one tangent you can discuss is circuit design, right? If you're going to go into electrical engineering, let's just say hypothetically you're going to go into electrical engineering and you want to design computers, or you want to just design integrated circuits, right? It's very strategic. It's not just about trying to build something that has a super fast processing power. It's about allocating processing in a smart way that's going to get a job done quicker, which isn't necessarily having just a really, really fast processing speed for linear processing, just for processing one-bit operations. That's not necessarily the way to do it. And that sentence will make more sense here, I believe, in a few minutes. But the problem we're looking at is a fundamental one in math and engineering. How do you go about, and this is going to be a totally different kind of problem than you've ever dealt with. It's not one, we're used to getting problems that have exact discrete answers in math, right? Everything we've done so far this year, we've been able to come up with an exact answer. It maybe took a little while to get there with integrals, but we came up with 2 foolproof ways of doing that. We could take a limit of rectangles as the limit went to infinity, right? The number of rectangles, which gave us an exact answer. And then that kind of collapsed into this great new trick called the fundamental theorem of calculus, which allows us to get there a lot more quickly, right, using antiderivatives. Both times, though, when we've had problems like this, if we've wanted to find the area under the curve x squared from 0 to 4, we get an answer, right? What's the answer? That's a bad one, too. Let me do, I don't really like that one. Let's do, that one's probably okay, actually. So what's our answer? 8. So I'm going to get x cubed over 3 from 0 to 4, right? which is what? 64 thirds. Okay? 64 thirds. Now, can I write that out? Can I write that perfectly as a decimal, as a terminating decimal?
No.
I can't. It's going to be a decimal that repeats. If I put this into a TI-84, which is kind of a wimpy calculator, I'm going to get the answer, what's that going to be? 21 and a third, 21.3 repeating. And it's just going to do like that. It's going to go for as far as the calculator, as many digits as it carries, it will carry it out with threes. It's not an exact answer though, is it? Now if I do this in a TI computer out CAS or a TI-89, it will tell me this is equal to exactly 64 thirds. There's a difference in the way they calculate those things, a fundamental difference. The TI-89 and the TI, what are they, the CAS ones, that means computer algebra system. What's the difference between a computer algebra system and the way this is done on Desmos or the TI-84, where we get a decimal answer?
Does it actually use algebra?
Yeah, the computer algebra system actually uses algebra. It's actually capable of doing algebra, smart algebra,
That's crazy.
which is pretty cool. I mean, that's the first one. I got a story about that too. The first one that was ever built was I can't remember if it was Mathematica or Maple, but it was built by an undergraduate at Stanford who was at Stanford when I was going to school there, and we actually got to like test the prototypes on this thing. It was really hard to use, but it was the very first one.
That's crazy.
Yeah, that was by an undergraduate. How about that? So when you're an undergraduate, you can do real stuff. I mean, you read about people doing real stuff sometimes where they'll do some research. So don't think just because you're an undergraduate, you can't get involved in some research with somebody and do important things. You really can't. So a computer algebra system, literally, it knows algebra rules, and it's going to manipulate the rules to come up with an algebraic answer, an exact answer. That's not what most graphing calculators do. What do most graphing calculators do? They come up with a decimal. How? Because on a problem like this one, it doesn't matter. I mean, there is no exact answer. In this one particular case, a TI-89 has no advantage over a TI-84 because there isn't an algebraic approach to this. They both have to default to the same kind of thinking. What do you think it is? You guys have the capacity to do this one. You just can't get an exact answer. But we have some experience with that already.
Does it do it geometrically?
It's got to do it geometrically. Yeah, it's got to add it up. It's got to approximate the area under the curve using some kind of an algorithm like we've done, right? We've done this before in the past where we took areas under curves and we added them up with rectangles, right? And before we got to the point where we said, let's take a limit as the number of rectangles goes to infinity, we didn't. We just took large numbers of rectangles. And if you think back to that, what did we find? We found that the larger the number of rectangles, the more accurate the approximation was, right? Okay, so we already have some experience with this kind of a way of thinking. And this is what we call numerical math. It's a numerical approach, meaning it's not an exact approach. We're just going to use the raw processing power of a computer to use really large numbers of rectangles, to process numbers quickly and get a decimal answer that is just arbitrarily close to the actual answer, meaning we can get it as close as we need to. So for your TI-84, I don't know how many degrees or how many decimal places it carries in its calculations. Let's assume it's like 16, okay? So then if you were designing the algorithms, and people do this, when they design these calculators, electrical engineers make huge amounts of money to go in and design the algorithms, and the computer programmers that are going to design the algorithms that the calculator uses to do these calculations. Now, if you use a TI-84, and we'll do this, there'll be some things I'm going to ask you to do in this class where you're going to make some calculations of areas under curves, and it's going to take it a while to come up with an answer. It's going to spin for a while, and it's literally going to process what's going on. I mean, it's trying to come up with an answer, but it doesn't have a tremendous amount of processing power, right? It's not a computer. It's just a little calculator. Everything it's got is built into a circuit board, right? And so it's not accessing hard drives. It's kind of limited, right? Because it's small and it's cheap. But they're trying, to give you a lot of bang for your buck. But these guys have got to come up with an algorithm for making these numerical calculations that's going to be consistent with the hardware capacity available to them on the circuit board. So it doesn't take too long, but it's also accurate, right? You would expect when you push the number in on your TI-84 that you paid $100 for, that out to 16 places, it's going to give you the right answer. But does it matter if it's correct out to 64 places? No, you can't see it anyway, right? So you just need to be accurate out to whatever the cutoff is for how many decimal places it carries with it on the calculations. Does that make sense? Okay. So that's the kind of thinking you would do, right? So our only experience is with rectangles. You think rectangles are probably the best way to do it? Probably not, right? I mean, maybe I can see one argument is they're easy to add up. But if you think about how the way rectangles match curves, and I should just pull up one of the old, one of our previous flip charts here rather than have to, I'm not going to do much with this, but if we're trying to match a curve that is pretty curvy with rectangles, they don't fit very well, do they? I could use left sums or right sums or middle sums even, where the height of the rectangle is determined by the middle of the interval. It's still, I'm going to get these rectangles that have, that don't hit the curve. They don't match the curve very well. Okay? Are there other shapes I could choose maybe that would be better?
Triangles.
Triangles. How would that work?
I have no idea. But if you, my reason I said that is because if you look at that first slope upwards, you could trace up that in a straight line, and then go back down at the same angle and be a triangle. And you could
okay, but now is that okay? When you said triangle, you're thinking the right thing, but it's not the shape you meant.
Just curious, can you use multiple shapes?
Can you say it again?
Can you use multiple shapes?
Okay, so you could, you want to come up with some formula, so to speak, that's not excessively complicated, because you're going to have to evaluate that formula for lots and lots of shapes, right? And so when we're done with this discussion today, you're probably going to look back and say, okay, well, man, we probably don't want to use more than one, right? But even now, you might get a glimpse of why that's gonna impose some pretty tough tasks on the calculator, right? So our goal is we want to get we want to find a shape that's going to do a good job of approximating the area under the curve, but it's an easy shape to calculate, for which we can calculate areas, right? What do you think? Trapezoids, that's it, exactly. That's what you meant, was a trapezoid, I think.
I was trying to figure out what that was called.
So it's going to be something like, because you're going to have this, all you meant was the top part of this thing, like right here, should do that, right? But the bottom part's going to be the same, right? This part down here is the same. Well, that side is parallel to that side, right? So it's a trapezoid. This side is always going to be horizontal, these sides will be vertical, but the top is going to vary depending on the curve. That's a trapezoid, right? Trapezoid is a great idea. Trapezoid matches the curve pretty well, and the areas of trapezoids are pretty easy to find, right? They're rectilinear shapes. They don't have any curvy sides to them, okay? So let's take this idea and let's see if we can come up with a way to generate a sum of trapezoids, put it into a reasonably simple formula that we could just add up. Okay, yeah.
Isn't that just a rectangle with a triangle on top?
Well, I mean, you could do that, but if you do a rectangle with a triangle on top, then you're asking for 2 calculations instead of 1.
So then what if we change the rectangle to 2 triangles?
How could you do that?
Now it's 3 triangles.
Bisect it.
Okay, but then one of them's not a right triangle, and it gets really tough, right?
Well, sure. We should do it like that, simple.
Here, come up and show me, Richard. Come draw it.
So you take it into 3 triangles.
So let's blow up. Let's take that one piece blown up. So let's say here's going to be the base that I'm drawing, right? And up here is going to be whatever the curve is doing. We're going to match with sub top. So how are you gonna draw that? You're making different color. There you go, all right.
So you have this triangle,
Uh-huh.
and you have two right triangles.
Okay, but you're right, but then those two right triangles, I mean, as long as I'm doing that, why not make it a rectangle? Because that's the easiest to add up.
What if
Well,
you
the
did a
triangle.
rectangle across the whole bottom half underneath that one line, the dip? That would get rid of like all of the area. except for the top.
Okay, as somebody who does a lot of programming, then I can tell you, this is when I'd look at that and I'd go, holy smokes, how am I gonna find a way to, over this curve, I've gotta, over the subintervals of each of these rectangles, I've gotta find the minimum, and then I'm gonna have to divide that up, so, see, this starts to get really complicated. I'm telling you, that starts to look, that's where I start to say, yikes, I don't wanna program that, that's looking pretty hard. Okay, so these are reasonable suggestions, but let's, and they've probably all been tried, but it turns out that the one that works out to be pretty easy is trapezoids. And you'll see why. The trapezoid rule ends up being pretty simple. Let's just take a quick look at it, and you'll get this. You'll see why trapezoids are easier than maybe you even think they're going to be right now. So if we are going to, let me make this, we're not going to look at, let's look at a couple representative subintervals. Let's say this is A, and here's our curve, right? And we'll take a couple of these in the middle, right? So we're going to go like that, right? We'll take a couple of these in the middle. We'll look at our first one, and then our last one. Okay, so we've already done most of the thinking. We've already taken care of a lot of this, right? We did rectangles, so we know how to deal with situations like this. If we call this A right here, we could say that this is x sub 1, and if this is the ith interval right here, then isn't this going to be x sub I right there? Agreed? Okay. And what was x sub I? X sub I was just A plus I delta x, right? Okay. So if I wanted to find the area of the ith trapezoid, well, first of all, let's remember what is the area of a trapezoid. So if we think about just, we usually draw our trapezoids in geometry like, like that, right? So geometry of a trapezoid, if these are the parallel sides, what do I call those? The bases, right? So we could call this B1 and B2. And what's the area of a trapezoid in terms of the bases and the height? So if we call that the height.
Is it height times base 1 minus base 2? No, adding them in some.
Yeah. Okay, all it is, and here's how you can always think, there's a really easy way to conceptualize
The average of them.
the area of a trapezoid. Think about cutting and pasting. If I were to, would you agree that if I were to slice that piece right there off and flip it around, it fits right there?
Yeah.
And if I were to slice this piece off right here and flip it around, it fits right there, doesn't it? Okay. Well, what's the length of this going to be then? I'm slicing it, so I'm cutting it right in the middle, right, at the midpoint of each of those legs. And so if that's B1 and that's B2, what's that distance going to be of the rectangle we created?
The average of
That's the average of the two, isn't it? Right? I'm cutting as much off of this one as I'm adding to the length of that one, both times, right? So it's simple. All this is just going to be the height times the average of the bases, right? No big deal. Okay. So now ours are flipped this way, right? They're flipped vertically, but if we're looking at the ith subinterval, let's identify what these heights are. Okay, so the left edge, this is going to be x sub I, this is x sub I minus 1, right? Okay, and this height right here at that point is going to be at x sub I minus 1 f of x sub I minus 1, right? This point right here is at x sub I f of x sub I, okay? And if I'm gonna add all these up, then what's this thing gonna look like? Well, the very first one, this is just a x sub 1. Actually, this might be easier. Let's just do this. I'm gonna make one little change to the way we're doing this. Let's start off, rather than trying to make this a fancy sigma, there's two ways you can do this, and I'm gonna do it this way. Let's just start adding these up. What's the area of trapezoid number 1 gonna be? And we're just gonna make a list. So a sub 1 is going to be, we'll just call it delta x, right? Delta x, that's just going to be the width of our interval divided by the number of trapezoids we make, right? Okay, and for now, we'll just call it delta x. We can always plug in values later for that. So it's going to be the height times delta x, or the average of the bases times delta x. What are the bases going to be? So it's f of a, right? So that height is f of a. This height is f of a plus delta x, right? Everybody agree? Okay. Or even just f of x sub 2, we could call it. So f of a plus f of x sub 1. We'll just even leave it like that. Divided by 2 times delta x, right? Okay, what's a sub 2 going to be? So we'll just add up a sum. Now the next one's going to be f of, so now we're on this guy. That was number 1, this is number 2. So the left edge becomes f of x sub 1. The right edge becomes, oh, that's a, sorry. So that's number 1 and that's number 2, right? So now the right edge becomes x sub 2. So we'd end up with f of x sub 1 plus f of x sub 2 over 2 times delta x, right?
The second half of x sub 2.
There you go, thank you. Okay, third one, you see a pattern here. The third one, here's trapezoid number 3. So the left edge now is x sub 2, the right edge is x sub 3, right? Okay, so we're going to get f of x sub 2 plus f of x sub 3 over 2 times delta x, right? Okay, all the way over to, let's do the last two. So the second to the last one is going to be the nth one, right? And this is going to be the n minus 1th one. So b is going to be the same thing as x sub n. This is going to be the point, or this is going to be the x value, the x coordinate, x sub n minus 1, x sub n minus 2, right? So the last two, this is the n minus 1. So that's going to give us f of x sub n minus 2 plus f of x sub n minus 1 over 2. So there's my average times delta x plus the very last one is the average of f of x sub n minus 1 and f of x sub n over 2 times delta x. And so this whole thing is the area, not a sub 1. We just added up the whole thing, didn't we? Right? Agree? Okay, there's n terms there. Is there a common factor I can factor out? In each one of these terms.
Delta x.
Delta x. In fact, delta x over 2,
Yeah.
right? Everybody agree? Okay, so we could factor out then so this is all equal to delta x over 2 times what? Well, if I factor out the delta x over 2, those are all gone, right? What's left? Well, now I've just got f of a plus f of x sub 1 plus f of x sub 1 plus f of x sub 2 plus f of x sub 2 plus etc. Right?
Is there a faster way to do this?
Not really. I mean, you're going to see the pattern here. No, you're not going to do this every time,
Okay.
but you're going to see a pattern here in a second. So yes, there is. There is. Is there a faster way to develop your understanding? I don't think so. I mean, I think this will work. Plus, if we take the last two of them, look what we get here. So we're going to get f of x sub n minus 2 plus f of x sub n minus 1 plus the very last one, f of x sub n minus 1 plus f of x sub n. Okay, did you notice something there in that?
There's two of all of every single one except for the last.
Yeah, look.
And the first.
There's two of each of these. They all come in pairs except the first and the last, right? That's huge, right? So if we know that, then we can rewrite this thing as a pretty simple sum. Because we know how to deal with f of x sub 2 and f of x sub 3 and f of x sub I, right? That's just, well, what's x sub I? Just a plus I delta x. We've known that for a long time, right? Okay, so all that stuff then, we could break this up into two parts. We've got this delta x over 2 times f of a plus 2 of each of these interior ones, right? I've got 2 times the sum. How would I write that interior sum? I've got 2 times f of x sub 1 plus f of x sub 2. F of x sub, how about f of x sub I? As I goes from what to what. So we had 2 of all the ones that started at 1 and ended at n minus 1, right? So we're going to call that the interior sum, and it's going to be all the terms from the 1th, or the first, not the 1th, the first to the n minus 1th, okay? But then I only get one of f of a and f of b. See what I'm saying? Right? And so if I were to, everybody get that?
Yes.
Okay. If I were to then get specific, like if I knew what f of x was and I knew what the number of trapezoids was, this would be easy to do, right? So let's do an example. Let's do an example. So let me write out the trapezoid rule. Say it again. Yeah. Yeah, this is, well, except for what's delta x? How do we define delta x always? Okay, so b minus a. So the width of the interval divided by the number of subintervals, right? B minus a over n.
B minus a over.
So then we could say trapezoidal rule. So this becomes b minus a over n times 2 on the bottom would just be 2n, right? That's what all this stuff becomes, right? Okay, times and then I'm going to write this differently than the book does, but here's how a lot of books would write this. They would write this as f of a, which is the same thing as x sub 0, plus 2 times f of x sub 1 plus all the way up through 2 times f of x sub n minus 1 plus f of x sub n, which is just b. Okay, why not call all that stuff in the middle, why not write that using sigma notation, right? That's what we should do, I think. So that's the one thing, I think the book is a little, that's literally how they write it out. We would add that up using sigma notation. So we should write this instead as b minus a over 2n. And usually what I do is I'll just group these two together. So we get f of a, x of 0, plus f of x of n, plus 2 times the interior sum. Sum of f of x of I, as I goes from 1 to n minus 1, right? That's, to me, is a simpler way to write trapezoidal rule out, right? Okay, so let's do an example. Oh, and what is x of I, by definition? So x sub I, if I'm starting at A, right? I start at A and I'm taking I steps of width delta x to get there, right? So A plus, I heard it, I delta x, right? So we could plug that in too if we wanted. And maybe we should, you know, but. So let's try an example using trapezoidal rule. So let's say that we've got, we want to approximate the area under the curve. Okay, and let's use, on this one, let's just use n equals, let's do n equals 4 and n equals 400. Okay, we'll try 2 of them. We'll try 4 trapezoids and we'll try 400 trapezoids. Okay, so what's the trapezoidal rule going to be here? What's f of x? You know that, right? What are a and b? 0 and 1, right? So if we want to add up the area under using the trapezoidal rule, we're going to get what? Do this one first. This one we could just add up manually if we want to, right? There's only 4 trapezoids. So we get, how'd you get that? Yeah, okay, so b minus a, 1 minus 0 over 2n would just be 1/8, is the number out front, times, and being as we're just doing 4, we could add it up using using that method, right? We're only doing 4 of them. So we can just add up first plus 2 times the second plus 2 times the third plus the fourth, right? Okay. So we're going to get, at least we have 3 more. So we're going to get f of a is our first one. So what's f of a? What's the value of our function at 0? 1. Plus, what's the value of our function? What's the value of our function at if we're going to break this into 4 parts? What's the value of our function going to be at 1 delta x, right? Because if we're looking at what x sub I is, right, it's just a plus I delta x. So x sub 1 is going to be 0 plus 1 times delta x, which is 1/8, right?
1/8 times.
Oh, sorry, delta x is 1/4, right? Delta x is b minus a over n is 4, right? Right, so if we're gonna evaluate this at 1/4, what do we get? Well, I don't know. Throw it in your calculator, somebody. What's 1/4 squared over 2 plus 1?
1 and 1/32.
1 and 1/32, so 33 32nds. Okay, so then we got to do this at 2/4, so at 1/2. So that's going to give us 1/8 plus 1, so 9/8. And then we got to do this at 3/4, right? which is gonna be, what are we gonna get? 9
Do we have to split?
eighths plus 1, so 17 eighths. Did I do that right? Is that right?
Wait, I don't think so. We could do
Maybe.
Right? I think that's right. 3/4, so 3/4 would be, oh, I'm sorry, 16ths.
like,
Yeah, whoops, I messed that up. So we're gonna have,
9 to 30 seconds.
yeah, so 9 30-seconds plus, so 41 30-seconds. Is that right? And then the last one, what would we get at 1? If we plug 1 in? 3's gonna get 3 halves. Well, we'll finish this. You guys are Let's do this. So that's our answer, right? Whatever that adds up to. Okay?
Are you gonna, am I gonna be able to get into here during lunch?